Welcome everybody to the Euro Wisdom Young Women 4OR webinar on learning, fairness and sustainability. So before we start, let me remind you that your camera will be switched off and your microphone too, but you will have a chance to unmute and show the camera at the very end. So it's the 3 Young Women 4OR and the experts who are basically showing their camera. So thank you very much, everybody, for coming today. As you may know, Euro Wisdom Forum is one of the 4 forums of Euro, and it provides a platform to support, empower, and encourage the participation of all genders in operational research within Euro. So we have mainly 3 tasks. So we make recommendations of best practices to Euro executive on issues women in OR face. We also promote championing, networking, and mentoring. And this is actually the reason for this webinar of women at the early stages of their career in OR. And we also promote a conversation around how OR can be utilized to help and create diversity and inclusiveness in our future. So having said this, I'm showing you here who were the awardees last year. So the 12 women for OR that we awarded almost a year ago. And today we have 3 of them presenting their latest research results. So the first one is going to be Maryam, who is at the Universidad Amsterdam. The second one is going to be Xishu, who is at Birmingham University. And the third one is Mirna, who is at the University of Zagreb. And as you all will know, in these webinars, we have an expert in the field. And today we have Professor Emilio Carrizosa from the University of Sevilla. So his main research interests are machine learning, industrial and applied mathematics. His research has been published in top journals in the field such as mathematical programming, operations research, etc. And he has also published in journals from other fields because he does multidisciplinary work. And that includes work in energy, hydrology, and chemical engineering. He has supervised 14 PhD theses, and 3 of them have been awarded different prizes. So apart from his research agenda, he's also committed to servicing the profession. So he's currently the president of MathIn and the president of the Spanish platform of technologies of modeling, simulation, and optimization in a digital environment. And he's leading various projects with funding, national funding and European funding, but also from the private sector. And to say a few more things, he has been the president of the Spanish Statistics and OR Society, and also editor-in-chief of the Spanish Journal of Operations Research. He's also coming frequently in mass media, such as TV, radio, newspapers, promoting the role of mathematics in society. So with this, I will stop sharing my screen, and we will have the first presentation given by Maryam. You have 10 minutes, and if you don't mind, I will let you know when you have 1 minute ago in case that you have not finished. So Maryam, if you could please share your screen.
Thanks, Dolores. I'm going to share my screen now.
Yeah, that's perfect. And if you can...
Thank you.
Yeah, that's wonderful.
Okay, thanks. So hello, everyone. My name is Maryam, and I'm assistant professor at the University in Amsterdam. And today I'm going to present one of my PhD works on learning to select operators in meta-heuristics using machine learning. This is a joint work that I have done with my PhD supervisors, Mehrdad Mohammadi, Bastian Paddu, and also Patrick Meyer. So first, I start my presentation with a brief introduction on how we can use machine learning for meta-heuristic algorithms in general. And then I will focus on one specific application of machine learning in meta-heuristic for the purpose of operator selection. There are different ways and categories where we can integrate machine learning inside meta-heuristic. So if you consider these two circles as machine learning and meta-heuristic, we have the gray part, which is the interaction between the two. And in my PhD, one of my work was to provide a taxonomy on different ways that we can integrate the two. So for example, we can integrate machine learning for algorithm selection, which means which algorithm works the best for a specific problem instance that we have, or for example, for initialization to generate the initial solution for meta-heuristics. I'm not going to go into details of this taxonomy, but today for my talk, I'm going to focus on operator selection. So we are going to see how we can use machine learning to select the operators inside a meta-heuristic. So let's start why we are dealing with operator selection problems. Whenever we have multiple operators inside a meta-heuristic, there's a need to select them at each iteration or stage and apply it to the solution. And there are multiple good reasons why we need to use multiple operators inside a meta-heuristic. First of all, there are different variety of operators based on the characteristic of a solution or the solution representation that we have. And each of them have different characteristics and work differently. And also considering the fact that the search space of combinatorial optimization problems are mostly non-stationary, so different operators may show different behavior at a different stage of the search. That's why maybe we expect by including multiple operators, we can improve the performance of the meta-heuristic. And also we know that the success of meta-heuristic is also really dependent on the selection of the operators. With this in mind, we have proposed a framework where we integrate Q-learning as a machine learning algorithm into the iterated local search meta-heuristic. So I just go into some details for the framework. In the left-hand side, we have a meta-heuristic algorithm. For now, we selected iterated local search because it's pretty simple and practical. So we have local search and perturbation repeated iteratively, but it can be any other meta-heuristic. And in the right-hand side, I have the Q-learning algorithm that we used for selecting the operators. So let's take a look on the Q-learning part. So Q-learning is a reinforcement learning algorithm where we have an agent that is interaction with an environment, and the agent tries to learn the best action under each state based on the reward that it receives from the environment. So it's somehow learning from experience. And the idea is to define a Q matrix based on the states and set of actions that we have for a problem, and then try to assign a value to these cells, or let's say the Q value, and try to update the value. So in this way, we can select the best action for each state. And for Q learning, we mostly use the Bellman equation to assign and update these Q values. Let's go a little bit deeper and see how really we can use this Q learning for operator selection. Here, for this algorithm, I consider that we have multiple perturbation operators, but it could be also multiple local search operators. But here I just selected perturbation operators. So we have a set of different operators called OPTP, and the set is called A. And at each iteration, we should select which operator to apply to the solution. And the idea here is to define a Q matrix and a set of state and actions. So for this algorithm, for this framework, we define the set of operators as the actions that are going to be selected at each iteration. And also we define the state of the problem as a very simple state. So state could be 0 or either 1. So 1 means that we had an improvement in the previous iteration of the search, or 0, it means we didn't have improvement and somehow stuck in the local optimum. And then the idea is to assign a value to this state and action, and then select the best action under each state. And in order to select the actions, or let's say operators, we use the epsilon greedy strategy, where we select the best action, or the action with the maximum Q value, with some probability 1 minus epsilon. And with epsilon probability, we also randomly select an action. That is to make a balance between both exploring action and exploitation of the set of actions that we have. And once we select this action, we are going to apply it to the solution. And once we apply it to solution, we will update the score, or the Q value of this action, using this Bellman equation. So this is the current score that is going to update it by some other values. And in order to use this equation, we need to define a reward. So here we define the reward based on the improvement in objective function, but it could be different ways to define the reward. And this is the process. So we select an operator, and then we assign a reward based on improvement in objective function, and then we update the Q values. And in this way, somehow under each state, we can find the best operator or best action to select. We call this framework QILS. We have Q learning and iterated local search. And we believe that this framework is general because we can use any other meta-heuristic with any type of operators. And at the right-hand side, we have Q learning. So it can be applied to different problems and for different meta-heuristics. And we generally need 2 types of data to work with this framework: the list of operators from the meta-heuristic and absolutely the value of parameters. And for the Q learning, we need a set of properties, the set of actions, the state, and the reward. And once we have this information, we can use the framework. For one of the applications, we just applied the problem to the permutation flowchart scheduling problem, where we have a set of n jobs, and we would like to process this set of jobs on m number of machines, and we are interested in scheduling the jobs and machines. So this is an NP-hard problem, so we selected for the first application. And then for the numerical experiments part, we designed 2 experimental phases. In the first phase, we are interested to see the effectiveness of this learning-based operator selection mechanism. And that's why we compare this QILS framework with random operator selection, which we call RILS, and iterated local search with only individual operators, IILS. And in the second phase, we are interested to see the competitiveness of the framework in comparison to the state-of-the-art algorithms. And for the data set, we use some classical data set for scheduling problem, which are Tyler data set and VRF data set. We have some small, medium, and large size data. If I would like to define and show you some results for the first phase, where we compare QILS with RILS and IILS, we compared it based on some different criteria. So the first criteria is the gap to the optimal solution. Here I showed only for 2 different instances. So 220 means 200 number of jobs, 20 machine, and 500 number of jobs, 20 machine. So these are considered large problems. And we have the gap to the optimal solution and also different algorithms. And if you take a look to the QILS and compare it to the other algorithms, we see that QILS has a lower gap compared to the random version and single operator versions. But that's not enough. We were also interested to see whether this Q learning part adds some complexity to the algorithm or not. That's why we just estimated the worst case complexity, and we figured out the QILS imposed some overhead to the algorithm. But this overhead is only dependent on the maximum number of iteration and the number of operators. So you see that it doesn't depend on the size of the problem. It doesn't grow with the size of the problem. So we can say somehow it's negligible. And also we were interested to see the computational time of the algorithms because we gave them the same number of iterations. From the overhead, from the complexity part, we expect to have higher computational time for QILS, but that wasn't the case, especially for some large instances. Despite the overhead, despite the complexity overhead, we had less computational time for QILS comparing to the other algorithms. But it's not true always, but sometimes that's true, especially for large instances. And the reason for that is that QILS, as shown in blue here, is able to converge better solution faster. So it finds better solution faster than the other algorithms. And
Maryam,
then
1 minute.
Yeah, and then we compare the competitiveness to 7 algorithms from the state of the art. And based on the gap to the optimal solution, we see that QILS is able to improve the state of the art. In average, all the algorithms on all the instances by 30%. So to conclude my presentation, I would say we provided a framework that is able to automatically select the operators. It's simple to use and easy to adapt to solve different problems. There's no need for training for that or no extra effort. And also the complexity overhead is not that large. And when we compare it to the state of the art, we have, let's say, a good amount of improvement. But there are still some challenges for this algorithm. We need to define a set of additional parameters for machine learning. We need to define the set of states, reward, and action. And I expect that they affect the output, the result that we get. And there's another issue when we have multiple number of operators. When the number of operators is large, then the Q matrix would become very large, and maybe it's more complicated to manage the space, the Q matrix. So this is something that we are for now working on to adapt the version to a case where we have numerous operators. That was my presentation. Thank you for listening to me, and I'm looking forward to your remarks and questions. Thank you.
Thank you very much, Maryam. So we will take the questions at the end. So now it's time for Xishu to share the slides and to talk about fairness.
Okay, can you see my screen? Is it the full screen?
Not yet, or at least I cannot. Now, yes.
Okay,
yes.
about now.
Yeah, perfect. Thank you so much.
All right. So good afternoon, everyone. Thank you very much for giving me this opportunity to present it here. My name is Xishu L. Starting from this week, I will start working as an associate professor of business analytics at the Birmingham Business School, University of Birmingham in the UK. I graduated from Erasmus University in the Netherlands back in 2019. So today I will talk about a stream of my current research projects for ensuring a social fair and economic inclusive gig and sharing economics. So due to the time limitations, I will only talking about the context of the problems, a little bit about the methodologies, and also what are the type of results that we have derived, and last, what is our contribution. Okay. So the gig and sharing economic is booming. It is disrupting many traditional industries, and it is in every aspect of our daily life. Here is some statistics about the scale of the business. So in 2023, and in the UK alone, 1 of 6 adults engage in gig work at least once a week. And I also show some famous sharing economic companies. You may find some more familiar than the rest. For example, Airbnb, Lyft, Uber, TaskRabbit. My favorite one is actually this new business company. This is called Borrow My Doggies. So who would have ever thought that your dog could also bring in money, starting to contribute to the rent? So the gig economic is a labor market featured by short-term work engagement. And the sharing economic is about the buying and selling access rather than ownership to goods or service. There are 2 distinct concepts, one emphasizing on flexibilities of the work and the other one focusing on ownership of the resource. But they are often interconnected and they can overlap in certain instances. One crucial element in both forms of economic is people and therefore their feelings. So due to the nature of the business, economic benefits are not enough for participations in these new forms of economic. So we all have a spare room at home, and our backseat in the car is often empty. So why don't we share? When I ask myself this question, it comes down to two things. First, I don't trust that sharing can really bring me benefit. This can be, I don't trust a stranger in my house, or I don't trust the platform, or I just don't trust that I really need that money. Second, I don't think this is fair because it is my house and I maintain it. Why should I give away more than 60% of the revenue to Airbnb? When contracting on a shared-based platforms, trust is how much the supplier utilized the information disclosed by the platforms. So the picture here is the first thing Airbnb will show to a potential owner, a potential suppliers, and that is the revenue forecast, and that is this number. So this information is critical as it directly determines whether the owner will join the platform. What is also important is how much the supplier will trust this information. As we all know, forecast is often manipulated across different industries. So trust will be a factor incorporated into this individual's utility assessments of the benefits and cons, influencing their decision to join a platforms. And in the gig and sharing economic, fairness concern refers to an individual's subjective evaluations of the situations about how fair it is. So this picture is what an Uber driver will see at the end of a ride. As you can see here, the passenger pays over $121. Uber takes over $65. That's more than half. At the same time, the driver takes the rest. So if you are the drivers, the question is, do you think this is fair to you? Of course, different drivers will have different fairness sensitivities that is based on their backgrounds, is cultural backgrounds or financial backgrounds. But as long as there is a fairness concern, this will lead to a disutility that will actually make them stop working from Ubers, which happens all the time. Because the people have feelings, once their feelings are hurt, they will no longer work for you. Based on the current situations, the goal of my research is about how can platforms in these new forms of economics build a sustainable marketplace that is both social fair and economic inclusive. And I have done 3 papers under these topics. The first one, we look at the one-time contracting process between the platform and the suppliers. We investigate what is the optimal information for the platform to disclose to the suppliers, and also how much revenue to give to the supplier. This is a joint work with one of my PhD students. She is also in her final year, so she's currently on the job market. So in this first project, we built a stylized game theoretical models with 2 players under 2 contracts. And these 2 contracts are the most common contracts in the sharing economics. Regardless of the contract, the decision the platform needs to make here is very simple. And that is, what is the information you want to tell to the suppliers? What is the promise? Your promise, what is your potential revenue if the supplier gives the house on your platforms? And you also need to tell supplier what is the revenue sharing ratio. So for example, I will take 40%, you keep the 60%, or if you maintain your house on your own, I will take 20% as the commission fee. So we derive the optimal contract under different situations, which is evaluated based on the fairness concern and the trust level of the suppliers, and also other parameters such as what is the business operation context. So how much can supplier tolerate a little bit uncertainty here? So here is just one example how we present the result. We also link our findings to the existing contracting theory. We use theory to explain our findings, or we contribute to the existing theory. And we also give managerial insights to platforms operating in this field. So that's for the first research. The second research, we extend our one-time contracting process to a long-term process, still between the platform and the suppliers. So here we look at what is the information sharing strategy, which is a policy according to which the platform should change the amount of information it discloses to the supplier over time. And our model is built based on Uber's current practice, and that is to give the revenue forecast every evening to the drivers so that the driver can use this information to plan their work schedule for tomorrow. And we model this long-term process following a Markov decision process. The platform decides at the beginning of each period how much revenue forecast to disclose to the driver, and the driver determines how much to work afterwards. Then demand will be realized at the second stage, and the driver updates his trust based on his experience, considering his expectations early on. Compared to the single shot problems, here the platform needs to consider the trade-off between the pros and cons of over-promising. If the platform over-promised about the revenues, the benefit is that the suppliers, they will come in and they will commit to work for Uber for longer hours on that day. But the disadvantage is that by the end of the day, the driver will only get paid if there's a passenger in the back seat. So this is different from how many hours they have been driving for Uber. As long as there is no passenger, they won't get paid. So by the end of the day, if they have been disappointed, then they will lower their trust for the next day. So maybe the next day, they will not log in on the platform anymore. And that is the issue that for Uber or any type of platforms should consider if they want to do the business in this field for the long term. And I think one more thing I want to mention is that after we model the problem for the Markov decision process, we derive the solution as the optimal stopping rule. We also try to find out whether there are consistent patterns in the structured policies. For example, is there any minimum level of trust the platform should maintain at all levels? Or is there a maximum level of trust the platform should keep in mind so that they don't overdo themselves? The third research here, we further extend on our previous research. So here we consider all three players in the gig and sharing economic, and that is the platform, supplier, and the buyers. And we look at what is the optimal sequence for building trust among these three players. And this is a joint work with Professor Ed Malthouse from Northwestern and with his PhD student In Han Pang. So the gig and sharing economics, essentially, this is a two-sided market. And because of this two-sided market, there is a network effect, actually two types of network effect. And the network effect is not only used to grow a market, it can also be used to build trust. So what we try to find out is that what is the optimal sequence to build trust in this triangle relationship? So you can imagine that if we are going to draw this triangle shape, where should you take your first line? Should you focus on the platform, between the platform and the supplier, or should you focus on between the supplier and the buyers, or from the buyer to the platforms? And what's next? Right, so it's just like if we want to learn how to dance tango, what are the steps? Or is there some optimal sequence here if we want to build the trust between three players, and whether the trust can reinforce itself, or whether there are any spilled over effect? If we build trust on one side, whether the effect can be also spilled over to the other side. So here are the three different working projects I've been working on. And also I would like to, one last slide is about what are the contributions we have done. So the first is that we provide a very comprehensive modeling framework to model the complex dynamics in the gig and sharing economic, focusing on the crucial elements of trust and fairness. And the second contribution is that we advance contracting theories by highlighting how trust and fairness shape the operational dynamics of platforms. We also further improve the understanding of contracting practice in new forms of economics and their implications for platform success and sustainability. And the last contribution is how we validate our results. I did not mention this at the beginning, but in each of the paper, in addition to the theoretical model, no matter it's a game theory model or Markov decision model, we always have one section which is called experiment validations. We applied our optimal result derived by our model to practice. And this practice is either a behavior experiment or is a field experiment. So what we want to find out is that whether our result can be implemented in practice, and also if we implement it, whether it really contributes to the society and the business. If not, we also want to explain that why this cannot be implemented, or what is the behavior bias here. So that's my contribution for the 3 research, and thank you for attending. I will wait for the question at the end of the presentation.
Thank you very much for your presentation. So we now move on to Mirna.
Hi,
So,
everyone. I'm
yes.
going to share my screen. Just
Yeah.
give me a second.
Yes, that's
Okay. Can you see my presentation?
yes, we can see. Is everything perfect?
Okay. Hi, everyone. My name is Mirna Gržanić, and I work as an assistant professor at Faculty of Electrical Engineering at Computing and Universidad Zagreb. I finished my PhD at the same university in February 2022. And today I'm going to talk about bi-level optimization in energy market participation. So here's just the slide about my department. We have established 6 laboratories, and I work partly in demand response living lab and smart grid lab, so focused on clean energy transition. So this is the brief content of my presentation. In the introduction, I will talk about why my job is important, so what we do actually to achieve climate neutrality. I will also talk about the difference between electrical power systems in the past and the now, and what is the role of final consumers, so of end users, in the clean energy transition and in demand response programs. So we are all bombed on everyday level with this transition to carbon neutral power system. What does it actually mean? So it means to reduce the greenhouse gas emissions, so to reduce their harmful effect on climate changes. We also want to integrate as much as possible renewable energy sources, increase energy efficiency, and as we know, since this last war between Russia and Ukraine, we faced a significant price increase in not only electricity, but also in gas. We want to diversificate the sources of energy supply. In this transition, the final customers input in the center. So this means that they have the free choice of supplier. They can choose between different electricity prices. They can participate directly on the market. They can be aggregated and provide flexibility services to the power systems through demand response programs, or at least install some low carbon technologies at their premises and become prosumers, so to actively produce and consume energy by their own. So the difference between the electrical power systems in the past and the now are several. So in the past, we had these conventional power plants that followed changes in consumption. They were flexible and they could adapt according to the changes that consumption or final users made. However, they are run on coals and gas, which does not contribute to the greenhouse gas, to the reduction of the greenhouse gas emissions. And to reduce that in this modern power system optimization and planning and operation, we are trying to introduce as much as possible renewable energy sources. With renewable energy sources, it became harder to manage and to operate the power systems because of their uncertainty and variability in the production, which leads to unsecure frequency stabilities. And that's the reason why now, when we want to turn down the traditional coal-based and gas-based power plants, we actually wanted to find the new ways of providing this flexibility when it's required to have balance between generation and production, and this is done with the final consumer. So with the changes in the consumption. So passive consumers now become active prosumers, which means they produce energy, they consume energy, but they can also adapt it, but they can also change their consumptions according to the need from the power systems. They also can install, as I said, renewable energy sources at their side, and if they have surplus of energy, they can share energy locally and trade between themselves. So to talk more about demand response programs and providing flexibility to the transmission and distribution system operator, so final users change their consumption behavior when they are either in two ways. So we have implicit and explicit demand response programs. What does this mean? In implicit demand response programs, suppliers or aggregators set different types of electricity prices, different values during the day, and then final customers react to these prices. When the prices is low, if they behave rational, then they lower their consumption. They increase their consumption, and during the period of high prices, they decrease their consumption. In explicit demand response programs, their consumption is directly controlled by the aggregator or by distribution system operator to ensure stable and secure power system operation. Of course, they receive some compensation or incentive to provide these flexibility services and to change their consumption profile. So here you can see these several pricing options. When during the day final users receive different prices, so they can schedule their electricity consumption and lower their electricity bill. Actually, this research was focused on describing what is the difference between implicit and explicit demand response programs. And first, I will talk about direct service activation or explicit demand response programs. Here on the top of the slide, you can see the objective function of the final users, which is to minimize their electricity cost based on the price received from the supplier. In this approach, we have two individuals' objective functions and two individual algorithms. In the first one, we minimize the cost of final users, and then based on this cost, the supplier participates on the day-ahead market and buys the adequate amount of energy for final users. In this approach, either the DSO or TSO, so distribution or transmission system operator, can directly control for example, battery charging or discharging as a flexible unit at the final user site. In this approach, we wanted to reward final users for providing this flexibility with reducing their network charges at the annual level by 10%. And the second approach is coordination through a via aggregator, in which we have one optimization algorithm, but it is formulated as a bi-level optimization model, which means that we have two objective functions. In the upper level, we have cost minimization of the aggregator, and then in the lower level, we have the cost minimization of final user. What does it mean? In the bi-level optimization, here we have actually a Steckelberg problem in which the upper level is a leader and then lower level is a follower. This means that the decisions which were made in the upper level, and here this is the price which is determined in the upper level by the aggregator and then sent to the lower level, have effect on the behavior of final users in the lower level. So this is not a linear model, and to implement it in the simple solver, it should be transferred into the single level. So it is done with Karush-Tucker conditions, and this means that to solve it with a solver, we need to have the objective of the upper level all the constraints of the upper level, constraints of the lower level, and then stationarity conditions, which are defined for each variable from the lower level, and complementary slackness conditions, which are defined for inequality constraints. So as you can see here, all of these equations are non-linear, so we need to use some kind of transformation or linearizations. And here we used Fortuny-Yama transformation and Big M method. It actually says that this list of equations in the second column, so they are linearized with this big M. This is like a big constant, and then the binary variable x, and the binary when this binary variable x is 1, it means that this equation will hold. So here are the results of our model. As you can see, we here have 4 types of consumer. We have a working couple, retired couple, students, and family. And we list on the right side what kind of flexible appliances they have. So it's either PV, so photovoltaic, battery, and shiftable appliances. And then we state if they participate or if they not participate in demand response program. So this is arbitrarily chosen. It can be differently, but for this type of problem, we wanted to compare which type of demand response program will be beneficial for final users with different type of low carbon technology. And as you can see in this cost graph, so for the consumer, for example, number 2, so this one does not participate in demand response programs and does not have either PV nor battery. So for him, it will be the same, almost the same, what type of approach he chooses. So if you're going to have 2 tariff pricing or some dynamic pricing set by the aggregator. However, if we focus, for example, on customer number 4, customer number 4 does not participate in demand response program, however, has a significant amount of PV production, and for him it would be more beneficial to have these dynamic prices and trade directly with the aggregator and not with the supplier under 2 tariff pricing options.
Mirna, 1 minute.
Okay. And then graphs below, we can see actually the difference between the prices which are set by supplier and aggregator. So on the graph on the left side, we can see that we have 2 tariff pricing options, so higher prices during the midday and lower prices during the night. And in this example, so final users are asked to reduce their consumption in our number 1, and then later on they increase their consumption to compensate what they reduced. And here we can see this red line, which states that this is the more dynamic price set by the aggregator when they not provide flexibility services, and this purple line when they provide. So these peaks mean they need to reduce their consumption, and then this valleys means they need to actually they have to increase their consumption. And this is it. This is my conclusion, but I already said some of these things. So depending on the type of final users and low carbon technology integration on their side, they can choose which approach is actually better for them.
Thank you very much, Mirna, for your presentation. So now we have say the thoughts of the subject expert.
Thank you. Before saying anything else, I would like to start, of course, thanking the organizers for giving me the chance of being here. I'm definitely honored to be a panelist in this session. I do believe that the role of women in science and technology should be stronger, and in particular in operations research. And one important step to make such role stronger is to give more visibility to researchers, to female researchers who are working in the field. So giving merits to those who are already working, and also to attract new young women to this field. So an initiative like this, in my opinion, is great, because it is going to be very helpful for our whole community to give female researchers the opportunity of being as visible as they should be. And also, I would like to thank, of course, the three speakers, because they have been making a very good job to compress in such a short amount of time so many things that they have been doing. Okay, learning, fairness, sustainability. These are definitely very nice words, but they are not empty words. They are crucial words in the world we would like to have, because we are all looking for a better world. But a better world is not only a world with more progress and more money, but also a sustainable and a fair world. And in such circumstances, I guess that learning, which is the third word that has appeared in the title of this session, is also fundamental. In one way or another, we may be talking about artificial intelligence, or in fact, we are also talking about operations research, the way we are able to build models, and we learn from these models to improve the mechanism of decision making. I have some comments and questions for the three speakers that I have found brilliant presentations. And if we go to the first, to Maryam, yeah, she has been working just in the bridge between machine learning and optimization, which is, in fact, we have the two ways. We can use optimization to improve machine learning procedures, because most machine learning procedures, in fact, they have behind an optimization problem. And Maryam has been doing the other way around. She has been using machine learning to improve some optimization, the behavior of some optimization problems. But a few questions I had. First of all, Maryam, in your presentation, you're talking about combinatorial optimization problems. My first question is it possible to go also to mixed integer nonlinear problems, or we have to be restricted to combinatorial optimization problems? So this is one thing. And related with this one is that in the end, when you're talking about the particular application in the scheduling, this problem is a problem which is more or less easy to parameterize. What can we do if we go to a more general combinatorial optimization problem? Is this doable, or we have to restrict ourselves to doing some sort of study for a very specific and well-defined class of perhaps combinatorial optimization problems? Can you give us some light about that?
Yeah, thanks for the questions. To answer your first question, it's possible also to use it for mixed integer programming or mixed integer problems. The way I use machine learning is mostly for meta-heuristics. Maybe that's why I just focus on combinatorial optimization problems, because maybe we are less inclined to use meta-heuristic for integer problems, or maybe we use some exact methods. So it could be possibly applied, but for my application and for this algorithm, I think it could be, it's only focused on meta-heuristic. So any problem that can be solved by meta-heuristic, we can use the machine learning for that. And for the second part, yes, the scheduling problem is somehow a simple problem, and the best algorithm for solving it is just based on some greedy algorithm, the iterated greedy algorithm. Actually, I think the performance of the machine learning really depends on the application. So for this framework, I also applied it to the traveling salesman problem, and the result was not that good comparing to the state of the art. So it really depends on the application and on the problem that you're solving. And maybe machine learning showed some good performance in some way, maybe, for example, to generate the initial solutions, but maybe for other ways, maybe to approximate the objective function, it doesn't provide really good solutions. So it really depends on the way of integration and also the application.
Okay, thank you. Another thing is that I find very challenging not only to define the set of actions and the set of states, in fact, the states which are the parameterization of the problem, but also I find also quite challenging to define properly the reward you're associating with the problem, because perhaps you can consider just the objective function, so the improvement in the objective function from one iteration to the next. But in case the different operators have different running times, this is perhaps something to be taken into account. I don't know how. And also now, which in the fashionable world of green algorithms, perhaps we are also interested in energy consumption associated with the effort for doing such an operator. Could you give us some ideas about how to go beyond just the improvement in the objective for going to the reward?
Yeah, that's also a good point, because it's challenging to define the states, actions. Actions is easier because you're going to select something, decide about something, and that would be your action. But state and reward, yeah, it's a little bit challenging. But I agree with your comments, with your remark about the operators with having different time. So I just saw in the literature they consider different type of reward, maybe improving the objective function, or just divided by the time that they assign to the operator, so make it fair, the comparison of the operators, and make the best decision. So there are different ways. We tried the simplest one and we saw that it worked. So for now, it's just the first framework that we presented. And as I said, there are some challenges for that framework that we're still working on to improve it even more. Yeah, I'm not sure if I completely answered your question, or I need to make it.
Definitely. And just the last question. Again, talking about the parameterization of for these problems. If you have a family of problems for which you have already used your Q-learning approach, and now you face a problem which is pretty similar but not the same, can you do some sort of transfer learning or something like that to use part of the information you have obtained, training for a class of problems to the next one? I guess that if the problem is completely different, the answer is not. But if it's just, you're talking about traveling system problems. If you jump from traveling system problem to some sort of traveling system problem with time windows, for example, could you use somehow the expertise obtained in the previous training? Do you have any experience about that?
The point is that the algorithm, the framework, doesn't need any training. So it learns online through solving the problem.
Okay.
And yeah.
Okay, I get it. Thank you very much, Maryam.
Thank you.
I would like to go to the second speaker, Xishu. First of all, congratulations for your new position.
Thank you.
And thank you for the effort of condensing 3 papers or 3 research projects into one single presentation of 10 minutes. So the effort to give a general framework and also to give hints about how to address the different challenges you have presented is impressive. Well done. I have a few questions, because I have been, in fact, with Dolores, we are working together in fairness, in classification and regression models, which is not exactly what you're doing, but one thing that we have faced is the fact that the definition of fairness is far from precise, and we find hundreds, perhaps, of different definitions of fairness. And you are talking about fairness in your approach. Could it be possible to have just a catalog of different precise fairness measures to be integrated into the general framework you are considering?
Yes. So that's actually a very good questions. I believe one of the reviewers also asked very similar questions, like what type of fairness you are talking about. So in our literature review of the papers, we have one subsections or one part just for fairness in the supply chain management literatures. So there are many different types. So I believe that the type that we are considering belongs to the category called distributive fairness. So basically, this is about some individual in the supply chain. What is their subjective evaluations of the situations? So that is how. So that's the difference between what they receive and what they feel they should receive. So what they feel they deserve. And then based on how they feel what the amount of money they deserve, there are also many different types of fairness, right? They can compare to other party in the supply chain, or they can compare what they have received to their expectations, or there's reference points in their mind. So then that will lead to many different fairness concerns. But what we did in this paper is just what is the real revenue generated from the content which is owned by the suppliers? Because that is essential of the sharing economic. You only rent out your resource. You are still the owner of the resource. So ideally, you should be entitled to have the entire revenue generated from your resource. But that's not the reality. The reality is that you only get a part of it. So we want to say that how big is the gap? For example, if the passenger pays for 100 euro, the driver gonna keep 80, and then there is the gap of 20. So this gap will times the fairness sensitivity of the drivers. And what we find, also other research find that the drivers or the suppliers in different regions, they have different fairness sensitivities. So for example, if you are from North Europe, so they found that usually people are not that sensitive to fairness. But if you are from Spain or Italy, so any small difference will make a huge difference on people's feelings, and that will influence their decisions whether to join the platform or not. So that's the type of fairness concern we have considered. But right now, because we are also implemented in a field experiment. So we actually observe that different people, even in the same region, they have a different reference point. And their reference points is built based on their previous experience. So for example, for the past months, I've been driving for Uber. I think that is a fair take. But now this week is different. So I don't think this is fair. So we also have been incorporating different types of fairness in our research.
Very interesting. By the way, I haven't been your referee. Be sure of that. I haven't been.
Okay. But we really like our reviewers, so just you know.
Another issue is that I guess that when you're coping with the utility functions of the different actors in the problem, I guess that it is not that difficult to build empirically, I would say, a utility function for the platform. As you're mentioning, if you have different users, different type of users or providers, how can you estimate their utility functions? Can you do some sort of inverse optimization in which, according to the decisions they have made, you can somehow forecast or estimate the shape of the utility function, or how is it done?
Yes, so in our theoretical models, the fairness concern trust level is a given parameters. So given that, we derive what is the optimal decision of the platforms, but in our validation sections, when we implement our results in practice, we need to know what is the real situation. So we first need to evaluate what is the fairness concern and what is the trust level in that region. So for example, right now we implement this field experiment in Rotterdam, in the Netherlands. In that small region, we have to evaluate that. So we have done so many different things. We have done surveys. We also have used their previous ride histories, and we can do this backward deductions to find out what is their reference points.
Okay.
But I would say that was not one of our contributions, because we use some existing literatures that how they calculate the fairness based on the empirical data. So we use the same method.
I'll say. Thank you very much. Thank you very
You're
much.
welcome.
And finally, Mirna, I have 2 questions for you, if Dolores allows me. I'm allowed. Thank you. So, Mirna, your contribution has also impressed me. It's very good. And one thing that is not fully clear for me from your slides is how uncertainty is addressed. So, do you have some sort of predict then optimize, so that you have first made all the predictions in a first stage and then you're having a purely deterministic model, or how are you?
No, I have a stochastic optimization where PV production, so production from photovoltaics, and non-flexible loads from final customers are modeled through scenarios. And then based on scenarios, supplier decides how to trade on their head market, so 1 day in advance. And then when each scenario, and then when one of the scenario happens and then the flexibility is activated, the DSO actually has the deviation from what he bought on their head market. And then if he cannot eliminate the deviation, then he will pay this balancing fee.
Okay, but the probabilities of the different scenarios are already fixed in advance, no?
Yes, they are fixed in advance.
Okay, thank you. Another thing is that you're considering, if I have properly understood, that consumers are rational. And as me, as a consumer, I am not, in the sense that I never pay attention to the publicity of the energy company saying we have an offer for you in the prices and so on. How is this incorporated in the model? I mean, is it possible to say we are offering these discounts or these subsidies, but perhaps some people do not take them simply because they ignore all the information given by the company? How are you working with this?
So in reality, actually, people who are, I would say, lazy and they don't want to change their consumption profile, they will never apply for that kind of services or for dynamic prices. But if they do apply, they can have more than just lower electricity prices. For example, there were a pilot project where the DSO actually gave a huge amount of discount on PV and battery for final users who are willing to participate or give, for example, 30% of their battery storage to the distribution system operator. And in order to react on the price signals, there are 2 possibilities. So the first one is that you receive on your mobile phone, for example, 24 hours in advance, the prices, and then you decide when the prices is low, you're going to increase your consumption. So you're going to put your dishwasher on, your washing machine and things like that, or you will charge your electric vehicles, or you have, it's called household energy management system, which actually does this EV charging and battery charging and discharging by default.
Interesting. Finally, the problems, the optimization problems you're facing, especially in the bi-level optimization problem, these are challenging problems. I guess that running times are gonna become large if the dimensionality of the problem is also large. My question is, what is the size of the population we may consider to make this doable? I mean, if we are considering Croatia, can we have a model for Croatia, or do we need a model for Zagreb, or just for a neighborhood, just with not with the computers a big energy company may have, but with the computers you might have, for example, in your laboratory?
Here, as you saw that we have 4 consumers. So basically it is not 4 consumers, it is 4 clusters of consumers that we are trying to represent for example, the whole neighborhood. And it would not be possible to consider each consumer because the problem would become computationally infeasible.
Okay, I see. Okay, thank you very much. Congratulations to the three speakers and good luck. I'm sure you're going to have brilliant academic careers or professional careers because you have the knowledge and the abilities to do good research and good presentation. Thank you very much.
Thank you very much, Emilio, and thank you very much to the three of you again for the great answers. I'm just going to show one more time my slides because before we open the floor, I would like to tell you and the audience that, of course, we organize more events apart from the Young Women for OR webinars, and I hope you can write in your calendar that we have an event on the 15th of December. This is actually our usual winter event. And this year is going to be a synergies event in which we are going to have also colleagues from WORMS and from WORM, which are two other organizations with the same aim as Wisdom. One of them is from the UK and the other one is from Informs. So they also take care of the visibility of women in OR, but in other parts of the world. Actually, at this point, I would like to also announce that the ALIO association, which basically puts together all the operations research associations from Latin America, Portugal, and Spain. They have also initiated another of these groups, and so we will be having synergies with them also very soon. And the second thing I would like to tell you is that obviously Wisdom is going to be present in the next Euro conference at the Technical University of Denmark in Copenhagen, in Lumbo, actually, in Denmark. And over there, we will have sessions from the Young Women for OR, but we are also going to have a satellite event, and you will be hearing from us very soon about that. And just last thing is please keep in touch with us. So we have a website, we have an email, we have a YouTube channel that is run by two of our very, very junior helpers. And we are obviously in LinkedIn and in X. So thank you very much for this. And now it's time for, a virtual coffee and for pictures. So I'm going to stop sharing. And please, if you have questions for the speakers or if you don't mind to also show your picture, because I would like to take a picture all together. Yeah, so that I would appreciate that we take the picture before the questions come. So
yes,
can we do that?
If you permit me, Dolores.
Yes.
Just to say that the winners of Young Women for OR in Copenhagen will receive their trophies during this section. So I will bring a big box.
Yes, thank you very much, Tatiana, for reminding us. So it's a very beautiful trophy that it was designed in Portugal. That's correct? Yes. Thank you so much for the reminder, Tatiana. So can I please, can everybody, show their picture? Yeah, thank you so much. Yeah. So I'm responsible for taking a good picture. Last time I didn't do that. I was told off by one of my OR colleagues in Twitter. Okay. I'm going to take one picture. Yes. And I'm going to take another picture to make sure that everybody looks great. Yeah. So thank you so much. Thank you. So now the floor is open for any questions you may have for the speakers. And in the meantime, I have to tell you that although Tatiana, Helege, and today are here from Wisdom to organize these webinars, there are many, many people behind. So people who, basically put the machinery to work. And I would like to thank all of them for this great cooperation that we are within Wisdom.
Indeed, thank you very much. And please invite your colleagues and your connections and join us who have not joined yet to LinkedIn and to other channels of Wisdom.
Okay, so I think if we don't have any questions for the speakers, one more time, thank you so much. Yeah, to the three of them. And thank you so much to the expert for all these great questions. Thank you to the audience because
Thank you very much for sharing.
Thank you to the audience because anything that we do, it's very important that you are there, coming back. And we really, really, really hope to see you on our winter event, and maybe you have to take, your winter, your Christmas decorations with it. Okay, so we will be in touch. So it will be announced very soon. So I wish the three speakers a great career ahead. I mean, it's already very great. But I hope this webinar and all the activities that we do will be helpful. And actually, we will be asking you about that, how helpful the whole year was for you. Thank you, everybody. And it was really, really good to see all of you.
Bye.
Bye.
Thank you very much.
Thank you.
Bye.
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 Hello, Jessica.